Hello everyone, good afternoon to all. So today we are going to discuss about the separation of no load losses of a DC missions. Okay, separation of losses in a DC mission. So here, if he goes to the uh, losses, okay, so these are the losses we are having the no load losses. So the no load losses are classified into two types. That is, one is the iron losses, another is the mechanical losses. Okay, so iron losses are classified into eddy current losses and hysteresis losses. So these are the mechanical losses. So mechanical losses are classified into two types based on that. That is friction losses. Another is the windage losses. So the friction losses are again classified into breast friction losses and bearing friction loss. That is, we are having the classifications based upon the types of where frictions occur. That is friction losses, windage losses. Right. So here, so first we'll talk about the. So here to find out the to sub to find out the losses. Okay, so the to separate the hysteresis and the current losses from the stray losses of a DC. Okay, so explain that separation of losses in the DC mission. So here first the classification we can see that the iron losses and mechanical losses. So iron losses are classified into eddy current losses and hysteresis losses. So mechanical losses, that friction losses and windage losses, right? So here to conduct this experiment we need the uh, shunt motor. So we'll conduct the mission, that is a shunt motor, and here so so here these are all are depend upon the speed. Okay, so if n is the speed, the hysteresis losses. Okay, so if n is the speed of the motor. Okay, so if n is the speed of the shunt motor, okay, or machine, so here the hysteresis losses. So here the hysteresis losses, so we can see, so directly proportional to the Bmax 1.625. Okay, that is, we can see that here. So here hysteresis loss are directly proportional to the flux density at the power of 1.6 into speed. Okay, so we can see the speed also depends upon the, okay, sometimes it is frequency. Okay, so frequency here not possible, right? So in addition, so that's will take in the uh, n, okay, speed. And similarly the eddy current losses. So the eddy current losses also is directly proportional to the maximum flux density into speed square. Okay, so from these two equations we are writing, that is WH is equal to, so we are taking the B max as a constant. Okay, so B power of 1.6 and B square maximum, so that we are testing the AN, and another is the eddy current loss is equal to the BN square. Okay, so we are taking as a BN square. So from this the flux density, okay, so the total iron losses is equal to, okay, so total iron loss is equal to AN plus BN square. Okay, so total iron loss is equal to AN plus BN square. Okay, that's your take. So these are because the we can see the iron losses are classified, right? The iron class are classified into different classes and hysteresis. So combinedly, that is we are writing, so iron losses is equal to AN plus BN square. Okay, so A is the B max, okay, flux density, okay, maximum flux density power of 1.6, and B square, that's maximum flux density square. Okay, so we are taking the constant values, that is A and B. Okay, so we are just taking the constant values, that is in terms of A and B. Now we'll talk about the mechanical losses. Okay, so here the mechanical losses, if we talk about the mechanical losses, so the brush friction losses. Okay, so the friction losses are, so the friction, so the friction loss depends upon speed. So here the mission, okay, if we take the rotor, so rotor will have the, so brushes, and so these brushes and bearings. Okay, so bearings, so the losses depend upon the speed. That's why, so the friction losses. Okay, so brush friction, so the mechanical loss also depend upon the speed. Okay, so we'll take that brush friction. So brush friction is directly proportional to the head. Okay, so if speed is high, okay, the friction loss also high. Okay, just for your concern. Okay, and bearing friction losses. Okay, so we are taking the bearing friction losses, so that is directly proportional to the speed of 1.5. Okay, and windage losses directly proportional to the speed square. Okay, square of the speed. So out of this is bearing losses are negligible. Okay, so out of this the bearing losses are next. Okay, these bearing losses are very less compared to the restriction and windage losses. So from this we are taking that, so here this we are taking, so friction and windage losses. So friction and windage, friction and windage. So friction and windage losses is equal to Cn plus Dn square. Okay, so just we are taking that. So friction windage losses are Cn plus Dn square. Okay, so Cn, so we are taking the, so this is the brush. Okay, so brush we are taking the Cn, and here windage losses are taken the Dn. Okay, so here you can see at the top, so the total iron loss is equal to An plus Bn square. So total friction minus loss, so Cn plus Dn square. Okay. So where C and D are the constant. Okay. So let's talk about the. So just take the consideration. So let taking the consideration. So let Pi is equal to total iron losses. Okay, and PFW is the friction and windage losses. Total friction and windage losses. So friction and windage loss. So PFW. Okay, and PNL. So total no load losses. Okay, so that is nothing but iron losses plus friction losses. Friction windage losses. So total power no load losses is equal to, so we can see that is Pi plus Pfw is equal to An plus Bn square. Okay, so this is for Pi. Okay, next for Pfw. Okay, so total no friction windage losses, we are writing that Cn plus Dn square. Okay, total windage and friction losses. Okay, so from that, so no load losses is equal to, okay, just we are taking the n as a common from this. Okay, so n square is common entry from both. Okay, so now we can write as n of a plus c plus n square of b plus d. Okay, just we are writing the equations. Okay, now we'll take the to separate these losses. So we have to find out the constant values. Okay, for find out the constant losses, so we are just considering the k1 is equal to. Okay, so we are taking this one constant, this is the another constant. Okay, so k1 is equal to a plus c, and another constant k2 is equal to b plus d. Okay, so no load losses is equal to k1 plus n, k2 plus n square. Okay, so by dividing the both sides n, by dividing by dividing both sides n, so then we'll getting the pnl by n by k1 plus k2 n. Okay, so just we are writing this equation. Okay, that is pnl by n is equal to n by a plus c by n. Okay, so n square of b plus d by n. Okay, n is n cancel and n square n cancel. Okay, so from that we're getting no load power loss is equal to pn is equal to it is, so a plus is nothing but k1 plus b plus d is equal to k2 n. Okay, that's we are getting. So this is about the k1 plus k2, right? So now we'll go to the experimental. Okay, so how we will find out in experimental way. Okay, so these last some, right? So this is our theory. So here we'll talk about, so at given excitation, so here we're taking the mission. So at given excitation, frictional losses, hysteresis losses are proportional to the speed. So windage losses, eddy current losses on the other hand, that is both proportional to the square of the speed. Okay, so that is we can see, so that is the n square, another is the uh, windage also is also n square, right? So that is we're getting the friction losses and hysteresis losses are right. So here, like we'll take the circuit diagram. So in the circuit diagram, so we'll draw the, so here it's like speed control of the machine. So just we'll take the machine, run the machine at off of the excitation. Okay, so here the machine having the excitation current of 0.9, suppose. Okay, so we'll take that. Okay, that is z value. Okay, so full excitation current that will have in the excitation current, that if is equal to 0.9 amperes. So here we'll do the two types. Okay, so we'll do taking the two cases. One is the off of the excitation, so another the full excitation. Okay, so we'll run the machine, so off of the excitation and full excitation, that is we'll taking the, so 0.45 excitation or 0.9 excitation, we'll run the machine, so both. So here this is the circuit diagram. So we'll run the excitation. Okay, that's off excitation, then we'll change the speed. Okay, so from that we'll draw the here, so off of the at constant, so we'll getting the voltage. So there's a current at the, we can see here, so there is a ampere high armature current, so voltage across the voltmeter. Okay, so voltage across the armature, okay, voltage across armature current, okay, speed and field current. So field current is the constant, so this is the constant field current. Okay, so then we'll find out the armature Ia square. Okay, so armature loss. So how armature is that? Okay, so we'll find out the Vi armature drop, voltage drop. Okay, so stray losses we are find. Okay, so that will be W by N value. Okay, so there is W by N is nothing but, so PL ln by N is that so we are taking, so PL is in terms of W. Okay, so W by N is equal to K1 plus K2 N. Okay, so this W is nothing but no load power loss. Okay, so no load power loss is indicating the W. Okay, so we are finding the W by N value. So if W by N value is known, we can find the constant. So here this we are taking the half of the excitation, and here we will taking the another full excitation. Okay, so depend upon the machine. So her machine will have 0.5 amperes full excitation, so we are taking the, so at constant excitation we run the machine. Okay, so these are the two excitations. Okay, one is the half of the excitation and it is the full excitation. Okay, so I'll getting the these values. So this tabular column for full excitation, this tabular column for the half of the excitation. Okay, see the armature voltage, armature current and speed, field current, that is the constants. We can see both. So two different, that is the half of the excitation and full excitation. So Ia square Ra. Okay, so here we'll find out the drop. So from that we'll take the stray losses. Okay, so here we can see the W by N. So W by N is equal to A plus C equal to B plus D N's. Okay, that we'll find out. So here, so armature is the, okay, armature sum of armature copper losses and above losses. Okay, so in the circuit diagram, power input is equal to armature. Okay, so power input is equal to VIA. Okay, so voltage into armature current, and in watts. Okay, armature copper losses are the, so armature copper loss is equal to, so armature copper loss is equal to Ia square Ra. Okay, so these are in watts, so we can getting the W by N is equal to A plus C plus B plus D N. Okay, so we can see is a K1 and another is the K2. Okay, so here we'll draw the graph. So the graph drawn between the W by N, and it is a straight line, and from which is A plus C and B plus D can be found. So in order to find the A, B, C, D separately, so let the field current can be charged. Okay, charged to the reduced voltage IR. Okay, and kept constant that value. Okay, so that is we kept the constant value, that is B plus D. If the voltage applied the armature before, we know the Wn is equal to A plus C n B plus D n square. So we can finally obtain A plus B and B plus D before. Okay, so C by C dash is equal to flux at normal excitation and flux at reduced excitation. That is, we are taking the full excitation and half of the excitation. Okay, how much flux is there? So we are getting the values, the d by d dash is equal to flux at normal excitation, flux at the reduced. So that is, we are taking the C by C dash is equal to, okay, so 0.5 by 0.35. Okay, so D and D dash same, so normal excited. Okay, so flux at, so we're getting the these values. Okay, so if you find to determine the C by C dash and D by dash, we can find determine the A B C D and, okay, so here how we are finding. Okay, so A plus C we are finding. Okay, so from the graph values. Okay, C by D, so we're getting the 0 point. Okay, C by C dash is equal to, so we're getting right, so shunt field current and shunt field, that is 1.6. So 1.6 is equal to, we're getting the 1.55. So C dash, okay, C value find out. Okay, Here these values will be found out by using the by drawing the graph, okay, at different excitations. So for w by n value and speed, okay, so we'll getting the straight line values, and we'll find out these for values, okay, we'll find out the slope, okay, by finding out the slopes we'll get the k1 and k2 values, okay. So by finding out the k1 k2, so we'll getting the values, that is a and b, c and d, okay. So this will be found out by using the separation of classes, that is we getting the test, okay. So by conducting this test we'll find, okay. So a plus c, we can see the graph, okay. So from the graph we are taking the different values, okay. So we can see the here iron and friction losses we are find out, okay. So here we can see the model graph, and if you observe this graph, okay, so here the graph we are finding the w by n value here, and this is for the speed. So here the speed and corresponding excitations we have drawn, okay. So we are taking the two excitations w by n values and find out the slopes, okay. So from the slopes we are finding out the uh, a b c d constant, okay. So we can see a and b n, okay. So friction and winder glasses, and for reduced excitation, okay, for full excitation and reduced excitation we have find out, okay. So we can see the procedure by keeping the excitation same value, that is say that half of the excitation now wrote on the reading. So for two different speeds, okay, by wearing the speed gear, okay. So restart at the, so wearing the restart in armature circuit, again vary the excitation other different values, okay. Say at the full excitation, that is we are run the mission at two different excitations, okay. From that we are taking the values, so you can see the voltage, current, speed, and armature losses, okay. Just we are find out the